Bacteria such as Escherichia coli, a friendly inhabitant of our gut, need amino acids to survive because, like us, they need to build proteins. One of the amino acids they need is tryptophan. If tryptophan is available in the environment, Escherichia coli will take it up and use it to build proteins. E. coli can also make their own tryptophan using enzymes that are encoded by 5 genes. These 5 genes are located next to each other in what is called the Trp Operon. If tryptophan is present in the environment, then E. coli bacteria don't need to synthesize it, so transcription of the genes in the Trp operon is switched off. When tryptophan availability is low, on the other hand, the operon is switched on, the genes are transcribed, biosynthetic enzymes are made, and more tryptophan is produced. So when it comes to the structure of the Trp operon, when you look at the picture, the Trp operon includes 5 genes that encode enzymes needed for tryptophan biosynthesis, along with a promoter RNA polymerase binding site and an operator binding site for a repressor protein. The genes of the Trp operon are transcribed as a single mRNA. Okay. The Trp repressor, so, okay, turning the operon on and off when it comes to what does the operator do? This stretch of DNA is recognized by a regulatory protein known as the Trp repressor. When the repressor binds to the DNA of the operator, it keeps the operon from being transcribed by physically getting in the way of RNA polymerase, the transcription enzyme, which is the transcription enzyme, you know. The Trp repressor does not always bind to DNA. Instead, it binds and blocks transcription only when the tryptophan is present. When tryptophan is around, it attaches to the repressor molecules and changes their shape so they become active. A small molecule like tryptophan, which switches a repressor into its active state, is called core pressor. Okay. So when there is little tryptophan in the cell, low tryptophan, on the other hand, the Trp repressor is inactive because no tryptophan is available to bind to and activate it. It does not attach to the DNA or block transcription, and this allows the Trp operand to be transcribed by RNA polymerase. In this system, the Trp repressor acts as both a sensor and a switch. It senses whether tryptophan is already present at high levels And if so, if it switches the operon to the off position, preventing unnecessary biosynthetic enzymes from being made. So, depending on the the situation, or if you're on this interest, you may also have heard about another form of TRP operon regulation called attenuation. Like regulation by the TRP repressor, attenuation is a mechanism for reducing the expression of the TRP operon when levels of tryptophan are high. However, rather than blocking initiation of transcription, attenuation prevents completion of transcription. When levels of tryptophan are high, attenuation causes RNA polymerase to stop prematurely when it's transcribing the TRP operon. Only a short stubby mRNA is made, one that does not encode any tryptophan biosynthesis enzymes. Attenuation works through a mechanism that depends on coupling, the translation of an mRNA that is still in the process of being transcribed. So let's talk about the key points. The Trp operon found in E. coli bacteria is a group of genes that encode biosynthetic enzymes for the amino acid tryptophan. The Trp operon is expressed or turned on when tryptophan levels are low and repressed or turned off when they are high. The Trp operon is regulated by the Trp repressor. When bound to tryptophan, the Trp repressor blocks expression of the operon. Tryptophan biosynthesis is also regulated by attenuation, a mechanism based on coupling of transcription and translation.